Okay, we're looking at another example of derivatives of exponential functions. Here we're asked to find a derivative dy dx implicitly. So if you remember what that means, here we have an equation of x and y, and every equation of x and y has some sort of graph. If the equation is a function, we could probably graph it on our calculator or maybe even by hand. But this equation with x's and y's kind of all over the place, it's probably not a function. But the idea here is that even if we have an equation that's not a function, it's something that has a graph. It might be a very strange graph, and I have no idea what this equation looks like when we graph it, but no matter what the equation looks like, even if it's not a function, the idea of the derivative still makes sense. I mean, if you pick a point on this strange graph that I drew, say right here, well, there's still a tangent line at that point, and that tangent line has a slope, so we would still want to be able to compute the slope of this graph. Okay, so we've done this before, but maybe go ahead and get rid of this little picture there. But the difference in this section is now we have some exponential functions thrown in. So if you remember, to take an implicit derivative, we want to differentiate everything with respect to x, both sides of the equation, and eventually we'll solve for this symbol dy dx. Okay, so I start by just taking the derivative with respect to x of both sides. Okay. There's the derivative of the left side and the derivative of the right side. Okay. Now we need just to break down the problem into little steps. Well, I've got a few things added and subtracted here, so of course a basic rule of derivatives tells me I can take the derivative of each term separately. So I'll go ahead and do that. Okay, so a couple of these derivatives are going to be, the true implicit derivatives. The other ones aren't so bad. So let's go ahead and start here on the left. Okay, we're taking the derivative with respect to x of x squared times y. Okay, now we can take the derivative of x squared and we can take the derivative of y implicitly. So we have to use the product rule here because we're multiplying those two functions together. Okay, so since we're multiplying x squared and y, the product rule, if you remember, it tells you to take the derivative of a product involving two functions. You have to take the derivative of the first term in the product. Okay, well, the derivative of x squared is 2x. Okay, and you multiply that by the original second term in the product. So that's 2x times y. And then we add the first function, the first term here, the first factor, x squared, times the derivative of y. Okay, and we're taking the derivative of y with respect to x, so that is dy dx. Okay, and I think this is maybe one of the things about implicit differentiation that seems confusing to a lot of people, but really what we're saying here is just not that much. Since we don't know exactly the relationship between x and y, if you ask me what the derivative of y is with respect to x, the only thing I can say is, well, it's dy dx. It's the derivative of y with respect to x. So that's the implicit derivative right here. Now this second factor was a function of x, a true function of x that we can write down. We have some rules for that, but we can only, in this case, we can only differentiate implicitly. Okay, so that one's done. Now over here we move on to the next one. We have to take the derivative of e to the power y. Okay. Well, in fact, I'll just kind of write it up here for a reminder. The rule we're going to use here is this rule, one of the main rules we developed in this section. Because if you look at what we have, what we're asked to do is take the derivative of e to a power. Now, if it was e to the power x, the derivative with respect to x would be e to the power x. Now, if we can't use that rule, then we need to use this one. If we take the derivative with respect to x of e to any power, okay, we get e to that power, so it's going to be e to the power y, right, that's our power, times the derivative of y with respect to x, okay, dy dx. I mean, this is in fact exactly that rule right here, but instead of the letter u, I've used a letter y. Okay, the point in this rule is that u is something which we assume depends on x, but we don't know exactly the relationship, so or maybe it's given to us, so this is how we compute the derivative. Okay, so since I don't know exactly what y is in terms of x, this is all I can say. Okay, now that's done. Now basically, I'd like to say right here that this is, all the real tough work is done, all the real calculus is done. The last two derivatives are comparatively pretty easy. The derivative of 4 with respect to x is 0, so I get minus 0. And then over here, of course, the derivative of 0 is also 0. And there we go. Okay. So at this point, we've taken all of the derivatives, and since they asked us to find dy dx implicitly, we've got to solve for that symbol, dy dx. Okay. So the way we do this is we move any term that doesn't have a dy dx, like this one, over to the right side of the equation, and then we factor the dy dx out of everything left over. So what I can do here is I'll just subtract 2xy from both sides. Of course, you can always subtract something from both sides of an equation. Cancels out right there. And then I've got x squared times dy dx minus e to the y dy dx equals negative 2xy. Okay, so both of these terms have a dy dx factor. I'll just factor it out, right? It's just something we're multiplying both terms by. So if I factor out that dy dx, I get x squared minus e to the power y, okay, and that's equal to negative 2xy. Okay, and finally, since we want to solve for this, we're multiplying dy dx by x squared minus e to the y, so we'll just divide both sides by that. Of course, you can always divide both sides of an equation by something, and here they cancel, and we get dy dx equals negative 2xy over x squared minus e to the y. Okay, so this formula, again, does the same thing every derivative does. It gives us a way to compute the slope of points on the graph of this equation. Okay, now the one thing we usually skip is the graphing part, because equations of x and y, if they're not functions, they can be very difficult to graph. But this equation represents some curve in the xy plane, and generally speaking, at points on that curve, there's a slope. Okay, to find the slope, no problem there. There we go. To find the slope, we just need this formula. Okay, dy dx is given by this formula. And of course, the usual difference of implicit derivatives, we see that typically with an implicit derivative, the formula for slope requires both x and y coordinates. You see x and y both appear here. Okay, so that's it.